All right, welcome to the people who were notified about the room change. So yeah, this is like a snow day, so this will be good. So we can really explore things now and take questions because there's not that many of us. So process management. We were talking about parents and children and that relationship, and today is how to maintain that and lots of fun stuff. But first, let's finish that example from last lecture with exec_VE. So we saw how to create a process that was through fork, where you have an exact clone of the current running process, and then the only difference is the return value from fork. That's the only way to differentiate them. So the way to execute a different program and start running it is with the exec_VE system call. So there is a C function wrapper for it, so it'll do the system call for you, but yeah, it's essentially a one-to-one, so there's just an exec_VE function. First argument it takes is a path that is the entire directory to get to a program. That will be an ELF file like we saw before because we are on Linux, and then it takes some arguments. So the first argument it takes is argv. So you can think of it as this is what you get from main if you have argc and argv. Well, the way that gets populated is from an exec_VE system call. So your shell would have, taken what you typed and converted it into this format. This format, it is an array of char stars, so it's an array of C strings. And the idea behind that is it's just supposed to end in null. So it's a null terminated array of null terminated character strings. So lots of fun. And then the other argument is environment variables called env. They're basically like global variables for processes, but we won't really get into them that much, just they're passed as another argument. For our purposes, there's some wrappers. So exec_VE is like the actual system call, but there's a few C wrappers that will take care of passing environment variables and stuff for you, so you don't have to deal with it. But for this case, I'll just say it is null. Now, how exec_VE works, that if it is successful, it will replace this process, load that new program, and start executing it instead. So if exec_VE is successful, this current process is no longer running this program. It is going to be running another program. In this case, it's going to be running ls. So that is one possibility. The other possibility is that it fails. If it fails and you read the documentation, it will return -1. So if it fails and returns -1, it would go into this if branch. Part of the spec of reading it is that it would also set this global variable called error_no. I save it here so I can keep track of the first error that happened, because this p_error function, if you read the documentation for it too, it also uses error_no. So there might be an error in printing as well. So I just want to save the first error that happens. This will take the current error_no and try and make it a more readable, give you some more readable output with what the error actually is. And then it would return, so this process will no longer exist. It will exit, because returning from main is the same as just calling exit. So in that case, this line will never execute in either case. So either exec_VE will be successful, this process will become ls, or it will go in the error case. There is no case that this printf line will work. So if I go ahead and execute that, I see that I get my first print message, I'm going to become another process, and then I get the output of ls. So any questions about that? Yep.
When you run any executable file in the shell, is that just running exec_VE basically, or doing a system call for that?
Yeah, so you might have noticed that even if you strace, let's go way back. It's lecture 2, I think. So even when we straced our little hello world example, the first line I told you to ignore from before was that line, but that's how the process started. So I didn't call that, but now we can kind of guess that our shell probably called it, because our shell would have had to create a new process. It would have had to fork, and then it would have exec VE'd. And that call is, yeah, from my shell. All right, any other questions about exec VE? So we can kind of tell what our shell does now. It would have forked, exec VE'd. Anyone notice something a bit weird here too? Why is ls there twice? Yeah.
Is it because, well, in the path, it's just the path to the executable, but in the argv, it's included as an argument?
Yeah, well, this is the actual program to run. And then, so for those of you that, hopefully everyone, that have written a main with argc and argv, does anyone want to tell me what the first argv always is? Or does anyone remember what it always is? Yeah.
I'm pretty sure like one of them is telling you how many arguments it is, the other one is the list of arguments.
Yeah, so argc is the number of arguments you have, and then argv is the list of the arguments. But specifically, what is argv at index 0, like the first thing? Yep.
The path to the executable?
Yeah, so one guess is the path to the executable, but the answer to that is no, well, in this case, it would be this. So ls would see this as arg0. You might see it as a path. Anyone else use it before and know what it says typically? So typically, it is just the name of whatever you type to run this process, which might not correspond with what the file is. So for instance, I could do that. So if I do this, so I can go ahead, do this. So I change the first argument. Still works, no problem. Yep.
So is it just like an alias to run that program, or?
Yeah, well, that's a good guess. So one guess is that, hey, is it an alias to run that program? So in this case, I don't have an alias called WTF, but there is a convention that is supposed to represent what you type to run the program. So if it was an alias, your shell would set that to the alias, and it's meant to represent how you actually executed the program. Yep.
So then in the proc folder where we see the processes that are running and the status, would the name of that program show up as what we put in argv there?
Yeah, so the question is, if I look at this in proc, will the name show up as whatever you have there? I believe so. So there's a few ways it gets names. So there's one way to set name, and then another way is that it looks at arg0, in which case it would be this. So I think the default name would be this, but there's also a different name that's slightly different that's based off the path. So this is, you might think this is a bit silly, but this is sometimes useful. So like for instance, there is like just one executable that does CP, ls, and everything, and it just changes its behavior based off what this argument is. And so it actually reads arg0 and actually does something different to it. Again, typically I said this is a convention. So like where it typically gets used is for help messages. So if I do something like this and look for the help message for ls, I see usage ls and then da 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 da. If I wanted to execute the same thing using exec VE, I would pass the argument here. And then I have a question, what does essentially this line do? This line just defines an array of characters supposed to represent the environment. I'm not going to define anything, so it's just a null terminated array. So if I just put a null pointer there, it means it's just size 0. So I'm not going to pass any arguments. So in this case, I will go ahead and do help, and then if I do exec VE this time, oops. Wait, why did it say it didn't save? Overwrite, I don't care. So in this case, if I scroll up to the top and see its usage, it will actually follow the convention. Let's see. So there. So it uses that name there. Is this the name of LS? Not really. It's whatever I told it I launched it as. So I could just set that to whatever I want. And one of the vulnerabilities is typically that's just a convention that's always set as the name of the program. Well, one day, so people have used sudo to like access, become the root user to do something. And lo and behold, it assumed that you had arguments, and someone did something like this to do sudo and just didn't pass anything. And sudo tries to access argument 0 without checking that there's at least one element, and that led to bad things where you could become root because you took over sudo because they didn't check the length of the arguments. They just assumed it was always true. So that is a fun topic. My screen died. Cool. All right, so let us blast through some of the content because we're going to get into more fun, gruesome names. So, oh, yep.
Trivial question, but if you don't have an argc, you can't pass anything from the terminal, right?
Yeah, so the question, if you don't have an argc, you can't pass anything from the terminal. And yeah, so your terminal, whenever you type things into it, it will populate that argv array and argc, and argc is just the number of arguments. So it could be 0 if you wanted.
Oh, okay, so if you don't have argv, you can't pass anything.
So yeah, so it's a bit different. So this is like a, go back. So the arguments for this is like a null terminated array of characters. For main, your argv is a bit different. Doesn't have a null pointer at the end. And the way it tells you how many elements there are is by argc. So it's a bit of a different format. But this will get translated into it by all the system calls and stuff like that. Yeah, so it gets translated. All right, so we saw that process state diagram before with the waiting state, which was also called ready, and the running state and blocked. So the Linux terminology is slightly different. The real technical details as it gets a little bit muddy, but in general, it kind of looks like this. You might have poked around in the proc file system already for lab 1. So in that, one of the things is called state, and it doesn't quite line up with our generic states we saw in the last lecture. And again, proc, every directory there, that's a number, that's a process ID or a PID. There's also a special one called self, which represents whatever process is currently accessing it, which is done by a bit of magic. But if you go off, read the states, you'll see something like this. There is a running and runnable state, which in our state diagram more or less corresponds to running and waiting / ready. So Linux doesn't really differentiate between the two. And then it has 2 block states instead of 1. So there is one block state called interruptible sleep, which we'll get into a bit more in the next lecture, which basically just means that that process could be woken up and it could do something. But it actually is waiting for something else to happen. And D, uninterruptible sleep, means that even if you poke and prod it, it can't execute no matter what. It's waiting for some network or something like that. So you can't wake it up whatsoever. And yeah, so you can tell, going for the chat question, your shell would, whenever you type something to run, your shell would translate what you typed, split it off into argv, and then call execve for you, and that's how it runs your program. So now if you really want, you know how to write a shell. So your shell just takes some input, forks, splits that input into strings, breaks it up into different string sections, and then calls execve to run that new program. You might notice 2 more states here that look a bit weird. So there is a stop state. So you can explicitly tell a process to stop executing and it will no longer be able to execute. We'll see how to do that later. And you might see this weird state called a zombie. That is a term the Linux kernel uses, and we will figure out how to create zombies today. It will be very exciting. So there's another question of like, okay, if fork is the only way to create processes, how do you ever create the first process? So the Linux kernel, as part of its process of starting, as soon as the kernel initializes all the hardware and everything, it launches one program and one program only and creates a single process. This process is special. It is called init, and by default, it is in /sbin/init, and it has the responsibility of launching every single other process on your machine. So every process on your machine, no matter what, will be launched by init or a child of init, and it could go on as deep as you want. But the ultimate grandparent or ancestor to every single process running on your machine is going to be init, and it is special because it has process ID 1. And what makes it really special is that, well, that's the only thing the kernel launches when it starts. And if init dies, well, guess what? Your machine is dead. That means you no longer want to run anything, and the kernel will just stop running. All your processes will die. Your whole entire thing will just die. So if it's dead, the kernel just thinks you're shutting down, so it'll just shut down your system. So there's lots of different things init could be. On Linux, on your systems and your VMs, it's something called systemd. Some people get into religious wars over it, but there's other options. The default one's systemd. For us, it doesn't really matter. You could even write your own init if you really, really, really wanted. We'll see what an implementation of one is. One simple one would be, okay, my init can just launch a shell, and then I have one shell forever, and that's the whole job of init. And then my shell can launch other stuff. So that could be a very, very, very crude estimation of what init does. Some operating systems might also have an idle process that the scheduler can run to represent your CPU being idle. So you might see that on Windows. Yep.
So you said that if init exits the kernel thinks your computer is shutting down.
Yep.
So can that be maliciously used?
Yeah, oh yeah. Yeah, the question is, oh, well, if init dies, that means your kernel, your computer's shutting down, so that can that be used maliciously? The answer to that is it could way back in the day, but nowadays it's protected. It will check access if you can actually kill it. If you can, you can probably also just type the shutdown command and just shut down the machine. So it's the same thing.
But is it like the moment it exits, your computer just like powers off, or? Like
So it wouldn't power off, but your kernel would be like, okay, we're done here.
your whole computer gets frozen?
Yeah, it would probably just get frozen. We'll figure out how to send things. You'll probably tell me to kill init, and yeah. Yep.
Wait, so when we first turn on a computer, that's like when it is created?
Yeah, so when you first turn on, so for instance, your VM, so because we're talking about Linux, after the kernel initializes all your hardware, it will launch one user process, and it will be process ID 1, and after that, your kernel's like, you take care of it from here, I'm done.
So like that's the like home page you get or like logging in and everything.
Yeah, so here we can see, so I have a slide for that. So here's like what a typical process tree looks like. So there is a child-parent relationship between all of them. At the very top, you'll see init. So init, part of the things, we'll see how to look around, but it would launch something like these. These are system daemons, so they're just doing some background work for system stuff. Then eventually you would log into your machine, so that would be a new process. So there is a user-specific systemd, which is supposed to manage all the processes for your individual user you log in as. So this would be what it looks like after you've already logged in. So after you log in, you get systemd for your user. Then for your VM, if you installed a desktop environment and you've logged into it, You would also see a GNOME shell. This process represents your actual desktop environment, what you see. And then through that, you might go and click Firefox or something like that. Well, guess what? That launches a process, and that process would be Firefox. It would be a child of that GNOME shell that represents your desktop environment. And then Firefox or Chrome, every browser, each of your tabs will be in its own process. So in this case, it looks like I would have 3 tabs open. And why would it do something like that? Well, remember, tabs are nice and independent and isolated from each other. So way back in the day, Firefox did everything in a single process. And if, say, you dereferenced a null pointer or something like that, that process dies, your whole browser goes down. That's not good. So that's why they re-architected it so that each tab is a new process. So if something horrific happens to one of them, it doesn't bring down your browser, it just brings down an individual tab. Yep.
So when you say like if it dies, the kernel is just shutting down, does that mean your computer's dead forever, or like you just like press power on?
Yeah, that means like you have to power cycle it again, and then it just restarts, and then everything goes back. Like what you guys made me do when you fork bombed me. All right, so yeah, other things that it could look like. So I might launch a terminal, and that would be its own process. Now, a terminal, that's responsible for taking what you type in on your keyboard, translating it to bytes, and translating it to essentially standard in, and then taking whatever bytes it reads from standard out and converting them to characters and drawing them so you can actually see them. And then as part of you interacting with it, that terminal would launch a shell, and that is what it looks like you're typing into that launches other processes. So our shell would be ZSH. In this case, I'm running an application called htop, which I will now explain. So if you want to see this process tree, you can run htop. It's a nice little process manager, which is going to be far more complicated than the one you're doing in Lab 1. And one of the other additional features it has is you can see the entire process tree. So if I go here and type htop and look, it will draw me a process tree. So at the top, I see init, process ID 1. I can see all of its direct children. Then I can see this process also has a child. I could scroll down and see that there's a lot of processes running on the machine. Here I can see some SSH thing that has to do with me, and that is running ZSH, which is then running bash, which is not what I'm currently doing, so that's kind of weird. There's a whole bunch of other processes that you are not expected to know what they do, but eventually we can see, hey, here's our good friend VS Code server. So I can see that this represents the terminal I'm currently looking at. It is running ZSH, and I am currently running htop. So I can see that htop is a child of ZSH, which is a child of my terminal, which is a child of some other stuff in VS Code because VS Code likes running processes. But you can go through, see the parent-child relationship for literally everything. All right, so with that, we will get into some gruesome fun. Oh, yeah, and so remember, processes get assigned a process ID when they're created, and it does not change as long as that process exists. It's just a number, and it's unique for every active process and any kind of dying process that we'll see in a second. On most Linux systems, the PID goes up to 32,000. On Mac, it's a bit different. I believe that limit is actually higher now on most systems on your VM. It's a configurable thing, so I think on your VM it's actually higher than that. Eventually, you might see that the process IDs kind of go sequentially, but they don't necessarily have to. It's just the way their algorithm works. Theoretically, it could do whatever, but computers just like doing things incrementally, so most of the time they'll be in sequential order. So whenever a process is completely dead and the kernel can recycle its process control block and process ID, another process can go ahead and take over that process ID. And also remember, thing in this course, that each process has its own address space or independent view of memory, and that's just another way of saying that each process has its own virtual memory. So you might hear the term address space. Yep.
Is the PID related the amount of space that like something has? So like, can we not have more processes running at the same time more than like the maximum PID?
Yeah, so that's a question. Can I not have more processes running than the maximum PID? And the answer to that is, yeah, no. Because if you run out of numbers, you can't assign anything to a new one, and then your fork call would probably fail. And also, like one of the defenses against the fork bomb, if you try and run it on the ECF machines, is they'll limit the number of processes you can create to something low, probably like 10. And then artificially, you just can't create any processes. You won't get assigned any process IDs or anything like that. Yep.
So if you call exec v, it says it replaces the program with a new process.
Yep.
Does that like give it the PID that it replaced?
Yeah, so if you do exec VE, it just replaces the process and its process ID stays the same. So no matter if exec VE succeeded or failed, doesn't matter, the process ID stays the same until it eventually calls exit. So yeah, it will stay the same. Yep.
For example, can we say that this number is what limits the amount of Chrome tabs that we can open?
So yeah, this would be a limit of the number of Chrome tabs you would running, but after 30,000 Chrome tabs, you're probably just going to run out of memory straight up instead of process IDs. So if that was like, if you were limited by the number of process IDs, it's configurable, so they would just say, okay, we'll just increase it until you run out of memory. So typically, this would not be the limiting factor. Yep.
Does PID correspond to the memory that's actually accessible?
Yeah, that's a question. Does PID correspond to the memory that's actually accessible? And no, it's just a number to refer to that process ID as nothing to do with anything special about it, except for process ID 1. That's the only thing that's any special whatsoever. And that's just the first thing that the kernel launches. Aside from that, they're just numbers. That, yeah, doesn't correspond to anything. Okay, so now we have to maintain parent-child relationships. So previously, I kind of cheated a little bit and neglected to tell you things because I had that little sleep in my parent to make things easier, so I didn't have to explain this part. But now we have to argue what happens when children and parents die in unintended orders. So, for instance, what happens if my parent process exits first and no longer exists? So my process, which is a parent, has a child process, and then I finish before my child. So in other words, the parent dies before the child. What happens to the child? It exists still. That's good. Yeah.
We could also, well, it depends on how you fork or XV, but you could just abort the process.
Oh, there's another. You could abort the process. The child. This child already exists, so it's like it's past that point. So this child's already running. It's it's however old you guys are. Yeah.
If the processes are like two different ones, how would the child one know that the parent one has died? Like, would anything change?
So the kernel knows which one dies, right? So someone knows, and if the parent's dead, well, what happens to the child? There has to be a parent-child relationship, yeah?
Does like another parent take on the children?
Yeah, another parent can take over. Is that what you're going to say? It's an orphan. That's actually the correct answer. Well, they're both correct. So there's an orphan, but that orphan needs someone to take care of it. So you can tell, this is the actual terminology, by the way. I do not write letters. I did not make this up. Like, this is the actual terminology. So that is true. So first, we have to talk about, well, why would it even need to be responsible? So remember, when you exit a process, well, you call exit and you return a number, and that number is supposed to indicate what happened to that process. So 0 if it was successful, and an error number anyways. So whenever a process exits or terminates, you can't actually reuse its process ID yet because someone needs to read its exit status to see what actually happened to it. So even though a process terminates, it still needs a process control block. So it might not be able to ever run again, but it has a process control block that stays around, and one of the things that would be in it is something like its exit status. So the rule is that if a process exits, someone has to acknowledge it in order for its process ID to get recycled in order to completely clean up the resources and completely delete it. Otherwise, you might get in the situation, like you might think, well, why don't I just, I have a child, I know its process ID, why don't I just pull it over and over again to see if it's still alive? Well, that doesn't quite work, because what happens if my child has a process ID of 60 or something like that, I look to see if it's alive, and then before I recheck process ID 60 again, my child could exit, and then if it was immediately cleaned up, well, then the kernel could reuse process ID 60 for some completely unrelated process that is not my child, and then I would read it again and be like, oh, my child's still alive, when really that process is completely unrelated to me. So that is why there's this acknowledgement step, because that's the only way the operating system knows that you're completely done with the process. You acknowledge that this is actually your child. It is now exited and terminated. You saw what happened to it. Now I can clean it up. So with that, there is two situations. So either you can have a child process and then it terminates first, and what is that called? That's called a zombie process. Again, technical term, we saw it at the beginning, and that is what it is. So a zombie process, why is it called a zombie? Because it's a process that's not quite alive, it's terminated, it can't execute anymore, it can't run, it can't do anything, but it's not quite dead because it has a process control block still. Someone needs to read its exit code. It's still consuming some type of resources, so it's not completely alive, it's not completely dead. Zombie is a perfect word to describe it. So that just means it's still around, it's consuming some resources, and we need to do something about it. And the other one is, like we said before, the parent exits first, in which case we have an orphan process. That child is now parentless. So the system call to actually acknowledge something is called wait. It has the following API. It takes an address to an int, and then as part of this system call, it will block by default until the first of your children has terminated, and it would acknowledge them, and then fill in that status with a bunch of information that you can query to see what actually happened to that child, how did it get terminated, and what are things about it. So wait will return a few things. So it will return -1 if it fails, like all the functions will pretty much see. It will return 0, which is an invalid PID, because by default, it will actually wait for a child to die. But if you don't want to wait and you want to just pull it and see, hey, do I have a child that's dead? Well, then there's an option to make it just query it and not wait around and not block. So that will return 0. In the case that we acknowledged it, we will get the process ID of the child that has terminated. So that wait status contains a bunch of information. We'll just look at the example. You have to use macros to kind of query it, and you'll have to read the man page for wait to figure out what you have to do with it. So if we go look at our wait example here, let's move this. So in this case, if I run it, oops, sorry, I will move this down. So I have main, it forks immediately, so it creates the child process, and we still have our parent process. Here, the child would get process ID 0, so in the child, I sleep for 2 seconds. It just goes to sleep for 2 seconds. In the parent, I printf that I'm calling wait, I create a local variable called W status, which is an int, which I will give it the address of, and then it will write a number to there that you shouldn't look at directly. You have to access some macros. But eventually, wait will return whenever my child has exited. So the child should exit after 2 seconds. It would come out of, it wouldn't go in the else branch, and it would return 0, which would exit the child. So the child should exit after 2 seconds. And here, I call wait, and then when wait returns, my child has exited. So this hopefully will happen after 2 seconds, and I will get the process ID of my child, which is now dead, and I can check. If you read the documentation, you can ask the W status it fills in, W if exited, so that will return true if the process exited normally. In our case, we'll just assume it can always exit normally for now. In the next lecture, we'll see other ways a process can exit. But if you read the documentation, if this is true, then you can read the exit status through this macro, and it will tell you the number it returned. So if we go ahead and run this, we should see calling wait. It'll wait 2 seconds for the child to die, and then it will say wait return for an exit process, gives us a process ID, which since it called wait and acknowledged it, this process ID now no longer exists because it can get cleaned up because it was acknowledged, and the status that we read. So any questions about that? Yep.
Above PID equals to 0, that's in the child process?
If wait returns 0?
No, from PID.
Oh, yeah, so this is a child process here. It just goes to sleep for 2 seconds.
Okay, and below that you have wait PID, right? So it's like it just waits until the child?
Yeah, so the parent waits until the child exits.
Oh, so the parent's waiting for like 2 seconds for the child to like exit.
Yeah, so in this case, because the child takes 2 seconds to exit, wait won't return until the child's dead.
Okay. Is that how wait works?
Yep. Yeah, so wait will return. If I had multiple children, wait by default returns whenever the first one exits. So if I launch a bunch of processes, I don't know which one's going to terminate first. The kernel will wake this up with whatever terminated first.
Okay, wait, so if you have like multiple children, then won't you have multiple waits?
Yeah, so that's a good question. If I have multiple children, well, if you're a good responsible parent, you need to acknowledge your child. So if I created 2 children, I need 2 waits.
Okay, 2 waits, each of them having their own numbers.
Yeah, they would each return the process ID of the child, right? And then you can query it. Yep.
So the PID 57896, now it's clean and like we can use it again.
Yeah, so that process ID is now, the kernel can reuse it for whatever it wants.
And it was for the child.
Yep. Yeah, and that was for the child process. And yeah, so in this case, wait won't return 0 because that's like the non-blocking wait. You can, if you read the documentation for wait, you can just have wait not wait until the first child to die, and it can just be like, return me the process ID of my terminated child if there is one. If there isn't, return 0. So that's an option you can have. Okay, yep.
So if the child calls wait, what happens? Like an infinite while loop, or?
Oh, yeah, so that's a good question. So what happens if the child calls wait here?
Yeah.
Something like that. So without running it, because I think I have to go quick, so wait will return an error code if you don't have any children, because the kernel knows all those relationships. So if you just call wait without a child, it'd be like, what the hell are you doing? You don't have a child. So I would get the same thing if I also like called wait again here. So I create one child, I wait once, now I don't have any children. And if I wait again, it's going to be like, hey, you idiot, you don't have any children, you can't wait. Yep.
So this wait function is just managed by the kernel
Yeah.
and not our program.
Yeah, so the wait, it's a system call. So it'll do that, and the kernel takes care of it. But you're responsible for calling it. Right, so that's part of being a good parent for your operating system. So there's the wait So yeah, what's a zombie process? So it's waiting, a zombie process, again, that child is gone and it is waiting for its parent to read its exit status. So there's a few things that happens. So whenever your child process exits, we'll see how it does this in the next lecture, but the kernel will poke you and say, hey, one of your children has terminated, you need to acknowledge it, and you're free to ignore that. You can be a neglectful parent if you want. So no one tells you, like the kernel prods you that you should call wait, but you don't have to. So yeah, and that is like basically a form of an interrupt. So the kernel will generate an interrupt to your process and say, hey, one of your children terminated, you should probably acknowledge it. And because it's an interrupt that you write, you can be like, yeah, no, I'm good. I don't need to. So yeah, in which case, the operating system has to keep that process control block around, and that's where it gets into that zombie state I talked about earlier, where it's neither alive nor dead. Yep.
So in practice, when you don't know maybe like how many children you're gonna have, and you don't know how many wait statements to put, do you use the interrupt? Like, do you rely on that to?
Yeah, so that's the question. So you said in practice, when you don't know how many children you have, is that an accurate statement? So waiting, you can only wait on your direct children. So why you say direct is because, well, you're the only one that can create processes, so you know how many you make, right?
But what if like the user is controlling how many?
But still, the user is interacting with your code. Your code's still making the processes. So yeah, if you lose track of the number of children you have, that's, like in real life, that's probably not good, right? So yeah, if you have children, you need to keep track of your direct children and say you were the one giving birth to the child, you'd probably know how many you had, right? So yeah, that would not be a great case. Yep.
In the example, the last example from yesterday, were you creating a zombie process?
Yeah, so that's a question. The example from yesterday was I created a zombie process, and the answer to that was yes. But they just kind of waste resources, so it's not a good thing, but my code was not great. So let's look at a zombie process. So zombie. So here's an example of a zombie process. So I'll do the same thing. I will fork again. Let's assume it's successful. The child's going to do the same thing, where it just sleeps for 2 seconds and then it terminates. Now, in the parent, I will go ahead and sleep for only 1 second, and then I'll get woken up. So I should be woken up while the child still has 2 seconds left before it terminates. And I will print off the child state. And then I wrote this little helper function that just accesses the proc file system and prints off the state that it finds in the status file. So I'll read the state, check for any error codes. Hopefully I can program and I don't get any errors, but always good to check. Then the parent's going to sleep for an additional 2 seconds. So it's going to wake up from this after 3 total seconds have elapsed. So my child will now have exited, but I didn't call wait or anything, and then I will read the child's process state. So if I read that, you should see that the term zombie is a real thing. So first time, it's sleeping, so that makes sense. It's still alive, and then after another 2 seconds, it's now in a zombie state, which the kernel keeps track of, right? It's not some word I made up. It's literally called a zombie state. So its process ID is still valid, but it can't execute or anything, and it can't get completely cleaned up. It's wasting resources. So if you just launched infinite processes and they were all zombies, then eventually you're going to run out of process IDs or memory, depending on how big the process control block is. Yep.
Can you scroll up a bit?
Mm-hmm.
No, the code. Just to understand what the code is happening, like you forked it, and in the else statement you sleep for 1 second, and then you check your child's process ID, right?
I checked my child's state, yeah, with its process ID.
And we are expecting the child to be sleeping.
Yep. So here, the child sleeps for 2 seconds and then exits. And then in the parent, I sleep for 1 second, and then I read its state. And then I sleep for an additional 2 seconds, so 3 seconds, so the child should have exited by then. And then I see it's a zombie. Yep.
What if like the children did not finish exiting after they sleep, and the parent like exited the program because of abandoned?
Yeah, so that is the next thing we'll do. So the question was basically what happens if the other thing happens where the parent exits first and not the child? Well, that's an orphan process and it needs a new parent. So yeah, the child process lost its parent process. The kernel is really strict about maintaining that parent-child relationship. The child doesn't die. It's like real life. Just because, you know, a parent doesn't exist anymore doesn't mean you die. So the child needs a new parent. It is called an orphan, and it still needs something to acknowledge it. By default, the operating system is going to reparent an orphan process to that special process init, which again is process ID 1. So we might have seen it before. Whenever I ran it, I saw like the child's parent ID was 1. Well, that was the rare case in that code where the parent exited first and it was an orphan process and it got reparented to init. So you can also think of init as the orphanage if you want. That is a good term for it. That is nicer than the real term. Yep.
If the parent created a child and that child created another child, so like the grandchild, and then the child in the middle, like the first child died,
Yeah.
that grandchild be assigned to init or the original time?
Yeah, so by default, whenever, like if there's a grandchild or something like that, the kernel only cares about direct relationships. So if you are an orphan process, you just get reparented to init. There is an exception to that though, and the exception is you can designate a process as being special to essentially become an orphanage, and you will accept any grandchildren that die and they'll get reparented to you instead of init. And that opt-in is called being a sub-reaper. So a nice gruesome name. And actually the technical name, orphanage was a nice name for init. Its technical name is the reaper, like the Grim Reaper. So yeah, so init, technically it's called a reaper. And now we know kind of the other part that would be in init. So init would just, a well-written init would launch some processes, and then whenever it's done launching processes, at the end of it, it would be like while true, wait. And then it would clean up any orphans it gets. So here is the orphan example. Let's do this really quick. So in the orphan example, we'll fork again, and in the child, we'll see whatever its parent is immediately. We'll sleep for 2 seconds, and then we'll check what our parent is again. And this time, in the parent process, we will only sleep for a second, so we will not last that long. And we can see that we have an ID, and then we see that the child's parent ID after the sleep is 1, so it got reparented to init. All right, any questions about that? Yep.
If a zombie's parent dies, does it then become an orphan?
Yeah, so that's a good question. If a zombie's parent dies, does it become an orphan? So yeah, that child process could be a zombie because the parent process just never acknowledged it. And then at that point, it would become a zombie orphan process. And then it would get reparented to init, and then init would acknowledge it, and then it would get cleaned up. Yep.
Is this why we were seeing the parent PID yesterday or the day before?
Yep. 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 Yep.
So we have to like manually call wait to acknowledge that the child died,
Yep.
and it does it automatically whenever the child is reassigned. So like if a zombie is reassigned to init,
Yeah, so the kernel will reparent it to init automatically. That's just part of what the kernel does. And then it would be init's responsibility to call wait. So because wait waits for the first process to die, if you just had while true wait, then you would acknowledge them as soon as they come in, right? As soon as they exit, you acknowledge them. You just do it over and over again. So the simplest init you could write would be like launch some process and then while true wait to clean up everything. Yep.
Can you explain here where the parent process gets killed? Is it during sleep?
No, so here the parent process just sleeps for a second and then it exits, and returning from main is the same as exiting, and exiting will terminate a process. Yep.
If I have a zombie parent, and that, sorry, if I have an orphaned parent and it gets sent to the Reaper,
Uh-huh.
what happens to the child? Does it also become orphaned and then sent to the Reaper?
So the question is, if I am a process and my parent dies, then yeah, then it would get reparented to a NIT, but your child is still your child. It would still think, it wouldn't get reparented to a NIT because you're still alive. Yeah, so you only get reparented when your direct parent gets terminated. Yep.
Yeah, so it goes in it, child, grandchild.
Yeah, if you want to think of it that way. But the kernel doesn't really care about grandchildren or anything. It's just parent-child. So it's like, where in this is the parent-child? So like here, oops. Yeah, so this would be just a bunch of parent-child relationships here. So init is the direct child or the direct parent of journal D, system D user, and udev or whatever. And that's all the kernel cares about. And the kernel just cares about this relationship. And if for some reason you break this, like if this process dies before this one starts running, this just gets reparented all the way to init.
So like if 597 dies before like the Firefoxes, the 946 Firefoxes creates the init with all of its children still connected to it.
Yeah, like if this one dies,
No, the one above dies?
this?
Yeah.
Yeah, so if GNOME shell dies, then Firefox would get reparent, then just this process would get reparented to init.
What happens to the other three?
So the other ones would stay. So this would just get reparented to init, and all these processes, their parent's still alive because it's just this one, so nothing changes.
So they're still connected to it. Like for them, nothing changes.
Yeah, for them nothing changes, just the direct parent changes. All right, I guess we're over time, so just remember, pulling for you.